Hello everyone. Welcome to lecture 9 of the LLM class. Um, just want to go through some housekeeping items here. Mini project 1 part 2 um, is due today. Sorry, this weekend. The Kaggle contest that got assigned on Monday, um, it shouldn't be a lot of extra work for you, but it's a way to consolidate your learnings. Um, So whatever you fine-tune your model, SBERT model and mini project part, or you can directly apply it and see what score you're getting. So the metric that's used here is mean average precision. It's a good metric for ranking. You know, when you want to rank a set of documents or rank a set of products, and you have like a ground truth ranking and you have like your predicted ranking from your model, how does the prediction differ from your ground truth? Like, for example, um, let's take an example actually. So that, I mean, you have some context for mean average precision is, so let's say I have the numbers 1, 2, 3, 4, 5. Let's say this is the ground truth and assume that the prediction is 5, 4, 3, 2, 1. Would you say the top 5 of ground truth and top 5 of prediction are the same? Yeah, so let's say 1, 2, 3, 4, 5 refer to the first product, second product, third product, fourth product, fifth product. If you're doing product recommendations, or if it's documents, it's a first document, second document, third document, and so on. So would you say the top 5 recommendations have the same recommendations? Yes.
Yes.
Yes. But would you say the order is the same, right? No, right? Suppose I ask the same question for top 1, you would say that's totally different. My best recommendation from prediction is way different from my best prediction for ground truth. So it's not just that you captured like 5 documents from 100 in the top 5, it's also the order of the capture that matters. So the Kaggle contest has this mean average precision, which looks at not just whether you captured a set of documents in a top 5 or top 10, but also the order in which you captured as compared to the ground truth. So it takes that into account. So that's where the ranking of the documents comes into play. So you can make a submission in the format that's given on the Kaggle page, and then you'll get a score. Once you make a submission in the right format, you immediately get a score, and you can see where, based on the score, the teams will stack up at different levels in the leaderboard, and you can see if you're in the top, that's amazing. If you're not, then it's a learning opportunity. It might just be that it's not necessary that you have to be in the top 5 or top 10, because many people could get the very good scores. So you could just like stack up from in the top 20. But if your score is way different from the top 5 or top 10, then that tells you maybe you're overlooking something, right? That's an indicator that you're overlooking something. Um, but just to give an incentive, the top 5 teams will get bonus points on the grade as well. So there's so many ways to earn bonus points on this course. Of course, you don't have to be in the top 5. That's not a requirement, but we do assume that you make a good submission. So if you made a submission that, like, suppose I make a random submission, like randomly rank the documents, you'll get a score of 0. So that's not a valid submission from standpoint of grading, right? So the scores do reflect whether your submission is good or not, but whether you have to be in the top 5 or top 10, that's a bonus, right? So don't need to stress about it, but again, take it as a learning opportunity. Like, it's an opportunity to understand how your submission changes the score. Yeah. And it's nice if you've done a casual contest of some kind. It's nice to add to your portfolio or your resume, right? Like, I did a Kaggle contest and this is what I learned. So it's an opportunity for you to dive deep and really understand what helped your submission get to the top, what tricks did you use, and all of that. So anyway, so you can use that as an opportunity. So that's about the Kaggle contest. Um, and then also wanted to check with you guys, how are we with the office hours, review hours, grading hours? Are you guys able to attend it? Do you, uh, are you able to get something useful? Do you have any questions on it? Okay. So if you do have questions, right, I do encourage you. I think the office hour timings are posted on the webpage. Sometimes you'll see it gets like the TAs might notify you 1 hour before, but you know the timing, so it's on the webpage. So if you miss any notification, you can just plan to go for the time slot that's provided on the webpage if you do have questions. Um, Anything else? Any other concerns or call outs or thoughts before we start?
Professor, is there a way we can do kind of evaluation of our result before submitting, like to have an idea how good is our, not waiting to see on the lead board, perhaps computing cosine similarity before generating the submission file and feel confident that we have good enough results, or what would be your recommendation, that what kind of
Well, you
evaluation?
you can you can have your own held out data set, and you can apply a similar metric like mean average precision on some ground truth data. So you'll have to kind of simulate it. So this is like how things get simulated, is you need to know, or you can even like manually rank it, for example, for a few documents, for a few queries, and then look at what documents are best fit. And you can use that and say, I will not use that to train or anything. I'll just use it to evaluate. And then you can see the successive model changes are actually increasing the score on that hand-picked data set that you have. That's one suggestion, right? So that can also help. Um, okay. Yeah. So, I mean, and there are other ways to do that as well. Um, so yeah, you definitely, I think you want to be able to understand in some way offline. You can use cosine similarity. That could be a base thing. You can also use averaging of embeddings and all the stuff that we've covered in the class before. You can use even better embeddings like LLM, OpenAI embeddings. You can do other things as well and see on different metrics how are you comparing, right? So yeah, and like held out test set is the best way. I mean, you can create a sample held out test set and then evaluate against it using the similar metric like mean average precision, and see how you're doing on that. Okay.
Thank you.
Okay, sounds good. Let's move forward. So we'll do a quick recap of the last lecture. We covered a lot of concepts and we went into a lot of details into the encoding transformer. So let's do a quick recap. And then after that, we'll actually switch gears today. We'll go into some prompt engineering principles and we'll do an in-class coding exercise around that as well. And some use cases for prompt engineering in different ways. Like, I mean, prompting is like, okay, sure, I'll send a prompt, but then there's like different use cases in there and different reasons and needs to do prompting in specific ways or other ways. So we'll kind of explore that today with a coding exercise as well. So you'll see in this lecture, right, we are toggling a lot between architectures. We also looked at some math last lecture. We're looking at ML modeling. Whenever we look at business use cases like Instacart or Amazon or other places where we discuss it, that's like the modeling aspect. Because you can know all of this, you can know all of the concepts and knowledge and still have gaps in, okay, how do I exactly apply it? Why should I use this or that? So thinking along those lines is ML modeling. So we also look at that. We look at business use cases and we also look at coding demos. So, different lectures will have different flavors. So last time was kind of architecture and math heavy. So today we'll kind of focus more on coding. So we'll kind of keep switching around depending on the lecture, right? Depending on the topics. So it's an ocean for a reason. This is like one of the Venn diagrams I found on the web, which may not be exactly, it may not be perfect, but it kind of highlights something, right? when you look at the area of machine learning and data science and AI, right? Like you see, okay, there is this computer science is sitting here, data is sitting here, and then math is sitting here. So you need all three in some sense to work on data science, machine learning, and AI. And you can say, okay, what's the difference between machine learning and AI? What do you guys think? Let's look at this one. What's the difference here? How would you define AI? So AI was actually, the traditional definition is AI is like any technology or algorithm that can solve complex um, problems that and also like uh, mimic human intelligence. So it stemmed from that space, right? So AI wanted like, the classic example was a Turing test. So it, have you guys heard of Turing test? Yeah. So Turing test is where if if an AI were to speak to you or a human were to speak to you, you would not be able to differentiate if it's an AI or a human, right? And like when the Turing test was, the concept came out in mid 20th century. Alan Turing was the one who came up with it. Um, People thought it's simply impossible. How can an machine mimic a human? Like human beings are so nuanced in their expression. And today, if you get a sales call from an AI, it might sound very close to how a human might talk to you, right? Some of the advanced AI bots that might make a sales call, and then they will go through all the specific steps to work with you and make suggestions and then get you to take an action so that you can actually move towards sales, and then even maybe crack a joke or two in between, and then it sounds really like a human. You might make out here and there that okay, maybe that's an AI that's making a sales call. So it's that good these days. So you can say AI these days, and at least in terms of language, might be passing the Turing test, right? Not in terms of reasoning, but definitely in terms of language. So anyway, so that's AI. We have machine learning. It's more methods, supervised, unsupervised reinforcement learning. So kind of like a lot of methods to help with AI. And then there's all these other things, right? Statistics. Like these days, we don't actually spend a lot of time on statistics, but there's a lot of statistics behind machine learning that goes under the hood. And there's a lot of math that goes under the hood. We looked at some math last lecture, but there's so much more. And then there's obviously data. Without data, none of these would make any sense. So there's also massive amounts of data. So anyway, so that's the reason why when we look at these topics, we'll toggle between math and coding and data and models and architectures and things like that. Okay, cool. So let's recap from last lecture. What was our learning and what did we take away, right? So we said that there is kind of a focus on two types of transformers. One is encoding transformer and decoding transformer. There's also the encoder decoder, and we said that's not really used these days because you can get most of your tasks done through one of these two. Encoding transformers are good for discriminative tasks, which is like the ability to discriminate uh, between different classes or be able to logically say, you're a cat, you're a dog, you're this or you're that, right? So classification, embeddings, semantic search, intent detection, all these fall under the realm of encoding transformers, and we focused on that with our assignments and mini project as well, right? And then comes decoding transformers, which are necessary for text generation like GPT, but can also be used for discriminative tasks. So that was a discovery that came about after GPT-3 on the decoding transformers became as powerful as encoding transformers. But before GPT-3, you would have to go to an encoding transformer to do an encoding job, right? Like embeddings, you would have to go there. But since the advent of GPT, even decoding transformers are able to do a good job. Um, and we also discussed the architecture behind encoding transformer. We said it consists of a multi-head attention and a feed-forward neural network block, right? And so this is like the this is one transformer block. So one encoding transformer block, right? And here we said it has like a self-attention and then it has feed-forward layers. Um, and we said that multi-head attention serves the purpose of putting the token in context of all other tokens, right? Why pay attention? Why do self-attention? Because I need to know what any specific token or word means. Like if I look at the sentence, I own a dog, it is out playing right now. If someone asks you what is it, you would refer back to this specific word, right? Otherwise, I don't know. If I just look at the second sentence, it's anyone's guess what it is, right? It could be anything. But given the previous word or whatever I have in the whole, it could not just be, it could be previous, it could also have to look in the future or in the next sentence to understand what it means, right? So here it refers to a dog, and that's why you need to pay attention to understand a sentence. To understand every word in a sentence, to understand every token in a sentence, you need to pay attention. So the mathematical formulation of that is what self-attention is. And we saw that self-attention happens through queries, keys, and values. Queries and keys interact with each other to bring the dot product and get that similarity, just like cosine similarity. The query and key of a token interact with each other. And then based on how much and then you also do a softmax, so you get a probability. So based on the probability vector, you decide, okay, I think it has to probably pay like 0.9 attention on this and maybe 0.01 attention on this and so on. So you get some weighted attention on different tokens for a specific token. And you do that for every token. So that's where we also said there's that attention matrix that's T by T size because this T token. So every token pays attention on every other token, and we need to know what that value is before we transform, before we transform one token to the next. We need to understand what the attention mechanism there is, right? And then we also said there is a layer normalization that kind of is additive in nature so that you don't lose what you had before, but you're just adding to it. And that works out well for training. And then we said feed-forward neural network is necessary because um, the tokens are non-linear transformed, right? And non-linearity can help with complex understanding of sentences. We saw this with XOR as our initial example. We said XOR can only be learned through a non-linear neural network, whereas OR or AND can be learned through even a single perceptron. So the idea of nonlinearity is that complex understanding or complex tasks require nonlinearity. That's kind of the basic idea. And we don't have any nonlinearity in self-attention. So it's captured in the feed-forward neural network, right? Okay. And we also look at the math behind feed-forward neural network and behind multi-head attention. And a lot of it is essentially like matrix algebra of layers of abstraction. And you can see like the query, keys, values, projection matrices, and ReLU are like the layers of abstraction. They're also like abstracted objects or building blocks that get combined with data as a source of truth through a loss function optimization, which you define depending on the task, uh, to then arrive at parameters that can then mimic a functional language model. So this is kind of like the summary, right? So you have some building blocks, you throw data at these building blocks, and the data transforms the parameters through these building blocks, which kind of makes sense at the high level, only at the high level. What's happening in detail, you'll have to look at the parameters and figure out what's exactly happening. But it somehow works out. You throw more data and then more learning happens and it starts to behave better as a language model. So this is like initially people would be like, let's explain it. And that was the area of explainable AI is you can explain what's happening with a model. Tell me why this AI made this decision. And you could do that with simpler models like logistic regression or even decision trees are very intuitive because you're making a decision based on a certain feature and you can say, okay, this is why I made this decision. But with these large language models and neural networks, it's hard to say why the next, why it made this prediction, what sequence of weights and transformations it went through, and then it arrived at this. It's hard to understand what's happening because it's so huge and so large and so nonlinear, but it kind of works. So that's why it's a abstraction, right? You put in a structure and you hope it works. And in this case, it kind of works. Okay. So let's do a quick in-class coding exercise. Sorry, in-class exercise. So this is not coding. This is an in-class exercise. Um, so it's a little bit long. And if, yeah, so you can also find this PDF on the web page, right? So let's say you want to do emotion detection by fine-tuning BERT on a data set. And one of the outputs of BERT pre-trained model for a given input is the last hidden state. This includes an embedding for every token that was passed into BERT. So if you have like 20 tokens, you have 20 embeddings in the last layer. Like you go through all the layers at the end, again, you're left with 20 tokens and their new embeddings, right? So that's the last hidden state. So let's say we're going to start with this last hidden layer and use that as input for a fine-tune model. So maybe you put some layers on top of it, and then you fine-tune like it's happening with SBERT. It could also happen with other, something else that you fine-tune on. So this in-class exercise is about the dimensionality of the inputs and outputs, right? So you understand how the dimensions work. So let's say you have sentences of the kind, I am looking forward to today. It's going to be a big day. This sentence conveys excitement, right? So we're looking at emotion detection. So I want to know what the emotion is. So in this case, this is excitement. So let's say there are 13 words in this input, and maybe using word piece tokenization, one of the ways to tokenize words into subwords, you arrive at 20 subtokens, right? And this is the input to the BERT model. So now the 20 tokens are getting transformed through this encoding transformer through multi-head attention, self-attention, and feed-forward. And it keeps going forward, right? And the last hidden layer includes an embedding for every single token. Let's say the embedding dimension is 768. Okay. Lecture 9 slides aren't on the. So the last hidden layer includes an embedding for every single token. So essentially you have like these, yeah, let's say token 1, token 2, token 3, and so on, token 20. Okay. So these are 20 tokens. And each of these, the starting embedding is also 768 dimensions, right? So that's where you started. Maybe you added positional encoding and then you transformed it and you did multiple layers. And then at the very end, the last uh, layer, what do you call this? The hidden layer, the last hidden layer has something like this. It has the same thing. So yeah, 20 tokens. So there are 13 words in this input, and using word piece token, okay, we covered all of this. For the purpose of emotion detection, you can either use a CLS token, which is a start token, or you can also average the embeddings of the token in the last hidden layer. So what's the So the question is actually very simple. What's the dimension of the pooled BERT embedding of this particular input example? What's the dimension of the CLS start token embedding in this example? And what's the total dimension of the hidden layer, right? So it's a very it's just orienting you to all these concepts so you can understand what each of these mean. Maybe just take a minute to think about it and you can put in the answer in the chat. We got that the last option is the right answer, which makes sense. The CLS token is the one that's uh, right in the front. So this is like the start token. And then the average embedding is like you just take all of this, sum it up, and then divide by the number. So you'll still get the same dimension. And that's why the second option is also the same as the first. And then the last option obviously is the total dimension. So that also checks out. So, okay. Um, One more question. Again, you can take a minute to think about it. Is why does pooling of the output need to be done for sequence classification, for example, emotion detection? So there's like four options here. Just think about it, and you can again put in your answer in within a minute. Okay, so hopefully you found that all of these make sense. So it's all of the above because yeah, for sure it reduces dimensionality. It averages context from all tokens. So this is an interesting one. Um, Here, people do use CLS token as well as like a pooled embedding, the start token, but you can also average it. In some sense, people have found you can either take the first token, which is not it's CLS token. It's not connected to any specific word in the sentence, but it's like the start token. You either that or you average out the embeddings of the tokens, right? Either one works. Um, and obviously, yeah, if you concatenate all of this, like you can still train a fine-tuned model on a concatenation, but then you're training on 15,360 dimensions. And then, if you had again a weight matrix of 1,000 dimensions, then you're looking at 15 million, right, computations. So keeping the pool dimension small will definitely help with fine-tuning of the train model. So that's another reason to kind of do this. So, okay, this also makes sense. Um, so we'll now switch gears. We'll go into some prompt engineering principles and walk through and look at some applications of like I mean, prompt engineering is like kind of a big area and there's a lot of hacks in there, but there are some common principles and common use cases that we'll kind of touch upon. Um, so we'll look into that in the next 20, 30 minutes, and then you can do a coding exercise based off that. And then if we have some time left after that, we can go into the next topic. So prompt engineering, right? Um, so of course, we're saying chat GPT use cases here, but think of it as any LLM use case of prompt engineering for natural language processing applications. So, I mean, you can do prompt engineering for anything. I mean, you can ask any question and say, hey, tell me what the weather is, and you get a response. So that's like general prompting that people use. Like even on Perplexity, you can go and start asking a lot of questions and you get responses. Um, like that's kind of like I want to understand the information, get some retrieval. So you can put that in this bucket, right? This is kind of the very common use case is just I want to get some information in general, not for any specific task, but just for my own personal use case or I mean, even it could be for a business use case too. You can also do that. So information retrieval is a very common use case. Uh, the second one is data augmentation. So this is a very interesting use case, and uh, you know, you'll find this is happening a lot in like very useful in industry settings. Because as you can imagine, even if you had like an LLM and you I mean, you have an LLM and you say, okay, I want to use this LLM for my company project or for some pet project. The LLM is not specialized to the area that you're looking at, right? I mean, I might be looking at building a sales AI bot, or I could be building a recommender AI bot, or whatever. You can build different kinds of bots that do different things, right? Or I'm building an emotion detection bot or whatever. So these bots are very specialized and they may not, like if you take a generic LLM and call it that bot, it'll do an okay job because it doesn't know the specific context that you have. Um, and also like you might have smaller tasks in your use case, like even emotion detection, for example. If you can make do with a smaller model, you want to kind of do that. But for that, you need some data. And then the question is, how do you get ground truth data? So data augmentation is very useful for uh, gathering like ground truth, like labels, right? Um, like if you say, hey, um, I'm uh, I'm like whatever, I'm not doing good today. Maybe maybe the emotion is sad or something, right? So you want to gather these kind of labels automatically so that you can train a smaller model. That's a use case. So you would prompt specifically to do data augmentation so that I can augment data and then I can use that data to then fine tune a model, right? If I don't have enough data, I can do that. And that's usually the scenario is I don't have enough data for my specific task. Then you can use this LLM as a ground truth and then you can do this, right? Um, like transfer learning is again related to data augmentation because you'd use data augmentation to do transfer learning, which is um, like, I mean, this can happen in small ways and big ways, right? Small and big use cases. Small use cases is just like, what we spoke about. I want to do an intent detection model. Where are my labels and where are my labels coming from? It's coming from this LLM model. And the reason I would want to use a smaller model when I already have an LLM, what do you think is one reason to do that? We kind of spoke about it in one of the earlier lectures too.
The compute, the
Yeah, it's a compute, the
cost.
latency. Like any typical AI, API call, might have some SLA. Maybe it'll be like 1 second or 2 seconds. But if you use a smaller model, you can, and you optimize it, you can even get it done in like 100 milliseconds, right? And so you can serve a lot of requests. So if latency is a concern, then definitely want to go with smaller models. Okay, so that's a small use case. What's a bigger use case of transfer learning that sometimes we are seeing these days as well?
Is it to learn more complicated tasks?
Yes.
For example, if you have something already specialized in like some basic task and you want to specialize it even further, you can use the transfer learning.
Yeah, yeah, you can. And there's even bigger use case than what you mentioned. Um, which some companies are happy about and some are not. Uh, it's the idea of knowledge distillation, right? So I can take a bigger LLM and then distill the knowledge that a bigger LLM has into a smaller LLM, right? And if that's okay to do, then you can do it, and then you can say I've kind of distilled the knowledge, and then I'm using this as a source of truth, and then I'm doing well. But sometimes it's not okay to do that. Like the recent news that we had, we don't know if there was some element of distillation involved, and you just have to check if it's okay legally to do that to take data from a bigger model and then train a smaller model with less cost. But in some sense, it's like you are using the bigger model as a source of data, even though you can say, and so that's the thing. So knowledge distillation is like it's a tricky space, and it's useful to do in certain cases, and then you have to kind of make sure you're not violating any laws in other cases, especially if you're doing it in a big way, or you're releasing a new model in the public and you say this model is so much better than, let's say, OpenAI or some other model, but then you actually use knowledge distillation, you uh, kind of like going around to get there, right? So that's like a tricky thing to, but if you kind of distilling like this distill BERT, it kind of distills BERT's understanding into a smaller model. That's okay. That's okay to do. So there are many cases that it's okay, but with the large language models, when there's a lot of competition and everything, it kind of gets tricky if you go ahead and do that. But yeah, I mean, these are kind of like the use cases to do transfer learning is to use the help of a teacher model to teach or train a smaller student model. So teacher-student relationship. Um, so again, how do you like you can use so the big use cases you just directly use an LLM and say you just keep giving me a lot of training data. I'll just use it. The other one is like, I already have data. I just need labels. Okay, give me the labels. Okay, that's, example like intent detection, emotion detection, and things like that. Um, and there could be more use cases as well. Like you can also use LLM. Uh, of course, this is actually not prompt engineering. This is actually LLM use cases, right? We're not looking at just uh, prompting use cases, but you can also get embeddings from any LLM and do semantic search. If you're doing with SBERT, you can also get Llama embeddings. You can get like the latest and best embeddings, and then you can also use it for semantic search, right? So today's focus will actually in this next 20-30 minutes, we'll look at like prompt engineering for information retrieval, and we'll also look at data augmentation. So we'll look at these two as our use cases. So let's kind of take a look at a notebook and walk through some examples.